All right, so video number 2 for the equations. Try to keep this one a little bit shorter. 15 minutes rambling is a bit much for anybody. So what we saw was that the equation for the cosine made sense. So if the cosine equation is correct, we want to take a look at some extremes for kind of conceptual ideas. If I've got a position graph and it is a cosine, those of you that are calc people know that the first derivative of the cosine is a negative sine, and it will look like the red graph that you can see on the screen. But why does it look that way? Why is it that all the boundaries and everything like that should match up? So on the cosine graph there, we want to point out where the maximum velocities are, or speeds. Let's think of magnitude of speed. And we also want to find out where the velocity is equal to 0. So where are those places? Well, velocity 0 should be the quickest one. An object will have 0 velocity when it is no longer changing position. And there's several places on the cosine graph where the object would not be moving. It represents position not changing as time goes by, and on a position graph, that's slope. So velocity is the slope of the position graph. So where's the slope 0? That's where our velocity is 0. And that would occur at these points right here. And of course at the bottom as well. And if you look at that, all those are happening at points, those points where there's 0 slope are at periods and half periods. So at the time 0, we'd have to have a velocity of 0. At time 1/2 t, or t over 2, half of the cycle way through. So this would be time 0. That would be t over 2. That would be t, 3t over 2, 2t, etc. So at those points where you have 0 slope, you should have, it should be at half periods. That's when you're at your extremes, because you start here at rest, you let go of the pendulum, it swings through, gets to an extreme over here, and it stops, and then it comes back. So at those extremes, the amplitudes is when you have the lowest velocities. So at those same exact times, we would then want to put zeros on a velocity graph. So if I highlight those dots where I had 0 slope on the position graph, I get 0 velocity on the velocity graph. Those are my 0 crossings. Now, that happens to be then on the velocity graph, pretending we don't have all the curves there yet. That means that we start at 0 and we then go to something else, we return to 0, we go somewhere else, return to 0 again. Starting to sound sinusoidal. What about maximum velocities? Maximum velocity would be mathematically where your slope is steepest on a position graph. So that means on a cosine sort of graph, the steepest portion is when you're crossing through the 0 point. That's when you're on that first part there, you're getting steeper and steeper down, and now you're getting less steep on your way down. That's when you do that 0 crossing. And that happens to be at a quarter of the period? We don't really care about whether it's at a quarter period or not, but that's where I highlighted in blue. And that happens to be a negative maximum velocity. And then on its way back up at about 3/4 of a period there, it also has a maximum velocity, but now it's a positive maximum velocity, and so on. So I'll highlight those points there on the position graph. Those represent V max. And so on the corresponding spots right down below on the velocity graph, we want to put in the maximum values. Now we don't know what the max is, but I can put a peak where then it won't get any higher and it'll start to drop down. Bearing in mind there that that first blue dot that I have right here, that first blue dot is a negative velocity, so I'm going to put a negative peak down below. The next one over is a upward sloping velocity. It's positive, so positive max. Then you get a negative max, positive max, negative max. And you start to see that cycle back and forth. Now, if I just had those highlighted yellow and blue dots, you would look like a zigzag, but we know it's got to be a smooth transition, so it ends up being sinusoidal. Now, from a real world perspective, if you have a pendulum, you pull it back. If it's passing through the position where it has zero amplitude now, that's when it's going fastest. It's been speeding up all the way down. Now it's going fast, and once it gets past that, it's going to start slowing down. So when it passes through zero position is when it has the greatest velocity, and we can see that line up on the two graphs. Now we're just going to kind of jump to the next one. We don't really need to go through and process it all, but the acceleration graph is going to look like the position graph, just flipped upside down. And that, again, we can go through and say that, well, we have zero acceleration when we're looking at the velocity graph, we have a peak or a trough and graph it all out like that. But in the end, we also want to make sure that we can see that the acceleration is somehow proportional to negative of the position. And the position is a cosine graph. So if you're looking at that picture, it looks kind of like a negative cosine, and negative of position should be a negative cosine. So those match up. Now let's go ahead and take a look at an example problem here that's going to ask us to calculate a few things, but really just interpret the graph of a pendulum. And I've got it drawn out with actual numbers. I've got the stock equation for the pendulum down there that, or for any oscillator, that x is equal to amplitude times cosine of 2 pi frequency multiplied by t, the variable t. And I want to know what the amplitude is, what the period is, what the frequency is, and then what's the length of that pendulum. Because from that information, I can figure out what the length of the pendulum is. So take a moment and see if you can get those answers. Now, amplitude, you just read the graph. Amplitude is the maximum value that you get away from equilibrium. And I've got it labeled there with that red arrow. And then down below, it's technically negative amplitude, but that displacement is the amplitude. So in this case, it would be 0.2 meters. The period is the time it takes to repeat a cycle. So if I'm starting out at 0.2 meters, and then it takes me all the way to that point in order to get back to the same position, that means that I can read that time and say my period is 2. Now, if I had something that was maybe able to move back and forth quicker or slower, if you had a different length pendulum, this graph would change. It would stretch and squish. So let's say we had a longer pendulum, it would take longer to go back and forth. I could just stretch this graph out and say maybe it took 3 seconds to go back and forth. Or if you have a really, really short pendulum, we could squeeze it in and say that it only took a second to go back and forth. Now that's going to help us with this idea of frequency that's next, because frequency is how many things per second that you're getting. And frequency should be equal to 1 over the period, or in this case 1 over 2 seconds, or 0.5 hertz, which means I'm getting half of a wave every second. And, or in this case, a sine wave, cosine wave, but you get half of a cycle every second. So in 1 second you go over to there, 1 more second you come back, 2 seconds for a complete cycle. But if I have something that has a shorter period, then if you just look at the graph, how squished together or spread apart are those waves? If you have a shorter period, the wave's going to be squished together quite a bit. And in the same amount of time, on that horizontal axis, that same amount of time, you got a lot more waves. If you have something that's a large period and it gets stretched out, then in some amount of time on that graph, you're not getting many waves. So there's that inverse between length of time and frequency of the wave. Now, lastly, we want to figure out what the length of the pendulum is. So on the pendulum, the equation for period is 2 pi times square root of L over G. And we're going to assume that we're on Earth, and G is equal to 9.8 meters per second squared. If you really want to, you could assume 10. But if we've got all those numbers, we can go ahead and calculate out what an answer is. We'd have 2 seconds is equal to 2 pi times square root of L over 9.8. And from there, you do a bunch of math and, well, I'll pause it and get to the answer in a second here. So I did a bunch of magical number crunching on a calculator, a real one, not a virtual calculator. And I get, lo and behold, that the length of that pendulum is about 1 meter. So what do you know? I'm probably planned that out. But yeah, you can see where these numbers come from. You can see where they go. And right now we'll go ahead and take a quick look at the springs. So for a spring, we're not going to go through and do the actual experimentation because I just couldn't leave you with springs. But we have seen springs before when we talked about Hooke's law and we talked about elastic potential energy. And we know that the force that a spring exerts to pull back on whatever mass is attached to it is going to be K times X, where K is a spring constant. It's measured in newtons per meter. The X measured in meters, multiply that together, you get newtons, which is force. But what we really want to take a look at here is the idea if you have, let's kind of make some predictions and some guesses. If I were to go through and do the same table of variables affecting the period of a pendulum, but now do it for a spring, what do I think might happen? And there are some simulations that I will assign you guys to take a look at online to play around with this. But for amplitude, it's kind of hard to figure that one out. You're going to have to just take my word for it here that the amplitude has absolutely no effect on the spring. So big amplitude, small amplitude, you get the same period. That should make sense, because otherwise if you pull something back a little bit, you get an period, you pull it back more, and I mean that would just cause chaos. It would just be impossible to figure anything out then. So the second thing on our list there is mass. So the mass attached to it. Now here we can process and logic through. If I attach a big mass onto the same spring, so I stretch the spring over, I let it go, it starts bouncing back and forth. If I put a bigger mass on there, do I think that the period will increase, decrease, or stay the same? More mass means more inertia. Inertia. Come on, I can spell. Inertia is the resistance to change in motion. So if I put more mass on that spring, it's the same force, but that same force is trying to move more stuff. So more mass means my acceleration acting on the block mass, whatever it is there, is going to decrease. And if the acceleration decreases, then the period is going to increase. It's going to take longer for it to go back and forth. You can imagine you got some little spring out of one of those like clicky pens, and you put something small on it, it goes, bounces back and forth. If you attach it to a brick, it's not going to have a very long, very short period anymore. It's going to take a really long time for it to move, if at all. Likewise, if you decrease the mass, you should get a smaller mass means less inertia, easier to move. Your acceleration rate should go up. And if your acceleration rate goes up, that means the time it takes to go back and forth is going to be less because you're accelerating faster. Spring constant. The spring constant is the force per unit length of spring stretch or compression. So if I have a stronger spring, if I increase the K value, that means it's going to be able to exert a bigger force, and a bigger force is going to mean a greater acceleration, which means the time is going to drop. And likewise, if I have a really, really weak spring, it's not able to pull very much, then I should have the period increase. It's going to take longer for that spring to move something if it's weak. So kind of going along the idea of what we did with the pendulum, I can say that the period should be somehow related to these two quantities that do produce change. For mass, it seems like it's sort of direct. So if mass goes up, period should go up. And for the K value, it seems to be sort of inversely related, or at least oppositely related. So that means my period should be something like this, something like M over K. That would make sense. More mass, longer period, more K, stronger spring, I should get a shorter period. Well, of course, the equation is not just going to be T equals m over k. The equation for the period of a spring is going to be 2 pi again, and now this time it's square root of m over k. So for, there's no mnemonic device for that, sorry, but the spring spring oscillator, we'll use that for a formula, and that is provided for you on an AP test. Now, if we go back and we take a look at that same equation setup, it doesn't matter if it's a spring or if it's a pendulum. If it's an oscillator, it follows this equation right here. We can use the same graph and now interpret that to figure out the spring constant. The only thing that's missing is I have to tell you what the mass of the object is, because that is required. So let's say the mass of the block attached to the spring is 0.1 kilograms. So we have a 100 gram mass attached to that spring. We release it, it goes, bounces back and forth. It still has an amplitude of 0.2 meters. It still has a period of 2 seconds, still has a frequency of 0.5 seconds, but now we want to figure out what that spring constant K is. So let's go ahead and use that period equation that we have. I want to make a cursive K there. So we can put in the 2 seconds equals 2 pi times square root of 0.1 over k. Now the 2's cancel out. We end up doing something similar to what we had with the pendulum. We'll have 1 over pi squared multiplied by k would equal 0.1, and then I can kind of process those things around and get to an answer that says k is going to be equal to 0.1 times pi squared. Let's see what that gets us. And wouldn't you know, it's like almost like I planned it. You get a k of about 0.99 newtons per meter. It's about 1. All right, another long video. Sorry about that. I just can't help but ramble when I'm trying to explain stuff.